solar mini-grids have turned from small pilots to an electrification wave. We were there when mini-grid regulation was established. When financial transactions were closed, we saw new technology thrive and companies fail. This is where we tell the stories. This is where we discuss the future. The mini-grid business, powered by INENSUS.
Hello everyone, this is Nico. Welcome to our podcast on solar mini-grid technology, trends and markets. I'm here today with my INENSUS colleagues, Dipta Majumder and Mike Arasa Ratemo, both mini-grid technology experts in our company. Dipta, do you want to start and introduce yourself quickly?
Yeah, sure, Nico. Hi everyone, I am Dipta Majumder, working as a mini-grid expert in INENSUS since 2018. I have been working in the mini-grid sector for some 10 years now, have worked a lot in Bangladesh for ITCOL, also in the mini-grid sector, and then I did my master's in renewable energy from Germany, and since then I have been working with INENSUS, mostly focusing on the sub-Saharan African market. Looking forward to this.
Thanks, Dipta. Mike, please tell us about yourself quickly.
Hello, my name is Mike Arasa. I'm based in Nairobi, Kenya. I'm a renewable energy expert. I've been working in the solar industry for the past 7 years, mainly focused in Kenyan industry. I have a master's in sustainable energy and environmental systems from Cyprus.
All right. Dipta, let's talk about system components in solar mini-grids. What type of system components do we need to consider when we think about solar mini-grids?
When we are discussing about an AC mini-grid setup, the key components are, of course, the solar panels, batteries, and inverters on the generation side. A diesel generator can be there for backup purpose, and for the distribution side, poles, conductors, and energy meters are the key assets. A diesel generator is typically needed as a backup when we have days with limited solar generation or battery backup. But as we see that as the batteries price are decreasing over time and the diesel fuel prices are seeing volatility in the market, we are, I think, poised to transitioning towards diesel-free mini-grids in the near future.
Yeah, and there are also many other aspects. Think about climate change. Nobody wants the CO2 emissions anymore, especially when you use donations, grants from donors. They usually require you to go without a diesel generator.
Exactly.
And other aspects are maintenance of diesel generators in rural areas. It's so much work and so much to follow up on. Every few hundred hours, you need to exchange the oil. You need to send somebody to site. You need to bring the oil. You need to ship the diesel fuel. The diesel fuel can be stolen. You need to protect that.
And also the transporting.
Transport is very difficult indeed. Yeah, there are so many reasons why to go without a diesel generator. And you already mentioned that this may be possible in the future, especially if we find a way to mitigate the demand risk, as already explained in one of our earlier episodes, for example, with edge computers.
Right.
Mike, Dipta already introduced the generation assets of a solar mini-grid briefly. Do you want to talk about how the world market prices for these generation assets developed over time?
So the cost of the key solar generation assets, which are the PV panels, batteries, and inverters, are significantly changed in the recent years, impacting the system configuration. When we're looking at the PV panels, prices have steadily declined since the early 2000s, driven mainly by the technological advancement and economies of scale and fierce competition among manufacturers. If you look at from 2010, a typical 60-cell panel cost around $2, while today it's closer to 20 cents per watt, representing a staggering 90% decrease over the decade. When we're looking at the battery aspect, like LFP batteries, a typical 5 kilowatt hours LFP battery pack costs are now around $500 to $700, compared to $1,000 to $1,500 USD just a few years ago, representing a 30 to 50% decrease. For the inverters, witnessed a decrease of 30 to 50%, whereby when you look at the 5 kilowatt inverter typically now costs 500 to 1,000 USD compared to $1,000 to $2,000 a few years ago.
Okay, and there's also new technology on its way to the market. What is that?
The new technologies currently that has shown the most promise is the sodium-based batteries, where they use the sodium ions as charge carriers compared to the lithium-ion batteries that are commonly used. Some potential benefits of the sodium-ion batteries include that sodium is more abundant and cheaper compared to the currently used lithium batteries, with a projected cost of around 40 to 80 USD per kilowatt hours, which is projected to go even below 15 USD per kilowatt hours in future. And with this in mind, sodium batteries are projected to make battery components cheap to around 20% of the capex.
Which is great, because in the past, batteries have always been the most expensive component and the component with the shortest lifetime. So therefore, the largest part of the cost was actually going into batteries. And this is changing now. Batteries are becoming a commodity with the LFP technology that you just introduced. We have already made a big step to the range of something like $100 per kilowatt hour on a cell level and maybe $150 to $200 on a battery systems level. And now if the prices are further going down with the sodium battery, we can potentially reach price levels of $100 per kilowatt hour for the battery system. And as you already said, like well below 50, 40, maybe even towards $20 per kilowatt hour on a cell level. Sodium batteries have been developed over the last year. And in China, you can now see the first cars deploying sodium ion batteries as their energy storage. And the slight challenge for sodium ion batteries in the car industry is that they have a lower energy density compared to the LFP batteries. So from a car batteries perspective, you have the NMC technology, which has the highest energy density, which is used in the high performance cars and the very expensive premium cars with very long range. And for the shorter ranges, LFP batteries are being used, and soon we will see in Europe, in the United States, but also probably in Africa, sodium ion batteries as the next trend, which have even a lower range in a car, but as stationary batteries in mini grids, they are ideally suited. And I'm really looking forward to seeing how sodium batteries will finally change the economics of mini grids. Mike, to what extent do you see Chinese inverters compete with European ones? We've also seen a lot of development on that end, and especially price reductions compared to the traditional inverters that you receive from Europe, like the SMAs, like the Studers, like the Victrons, and so on. Do you want to tell us more about that?
Yes, when you're looking at the Chinese inverters currently, they have approached like a tier system where they have brands like Huawei, Sungrow, and Solis, which have heavily invested in R&D and offer inverters that comparatively are at par with European brands in terms of quality and performance.
And also price?
So when you're looking at prices for the Chinese inverters, we are looking at price difference of 15 to 25% cost advantage compared to the European brands, which is mainly to the access to the lower labor and material costs, which is a significant factor for budget cautious projects when you're looking at the Chinese inverters.
Okay. And then you said there is a second tier and maybe a third one. Do you have some insight on what's happening on that end?
So the second tier brands typically offer the cheaper inverters, but often compromise on quality and lifespan. Also, warranty is limited. Like for instance, here in Kenya, we have brands like Mast, which normally, typically the lifespan you find that it's between 2 to 5 years. However, the warranty also you're given like 1 year warranty compared to Huawei and Sungrow brands, which can give 5 years and also offer extended warranty options.
Up to 10 years, like SMA, for example, or which range?
Yes, up to 10 years.
And these inverters that you're talking about are battery inverters that are single phase and can be combined into 3-phase clusters?
Yes, they're typically single phase inverters clustered into the 3-phase. Yes.
I see. Do you have information about what the maximum system sizes are? These maximum system sizes have in the past been kind of a challenge for some of the European brands, for Studer, partly also for Victron, for example, compared to SMA. Have the Chinese vendors overcome that challenge?
On maximum system size, like for tier 1 brands like Huawei, Sungrow, like recently I saw Sungrow have grid inverters of up to 350 kilowatt. Yeah, so on size, I would say they're a bit more flexible compared to the European brands because, like for instance, most recently when I look at Schneider Electric brand, like here in the Kenyan market, we're looking at a maximum size of a 50 kilowatt inverter.
I see, like clusters of 50 kilowatts or one individual inverter?
Yeah.
Clusters, yeah? Okay. Good. And another challenge that I have faced in the past with some inverter brands was that these inverters could just connect to one large battery bank. Even if you form clusters, they all need to be connected to one large battery bank. And this, of course, makes it difficult to expand the system in stages. It's easier if each cluster has got its own battery bank, and then you can add another cluster to add additional capacity. In the other option that I explained before, you would need to add new battery strings to an existing old already cycled battery bank, which is very tricky, not only with the old lead acid technology, but also with the newer lithium ion technology. What is your take on this, Dipta and Mike?
Yeah, some years back, the most common design for mini grids were this cluster based, like as you mentioned, Nico, that they're using single phase inverters and making this like 3 of them and making this like a 3-phase system, no? And each cluster would be tied to 1 or 2 battery strings, and that's difficult to scale. But nowadays we are seeing that the mini grid developers are shifting from this idea and are rather using larger 3-phase inverters, as Mike mentioned, in the range of some 30-50 kilowatt.
And that is then individual inverters, right? In that range that are still modular and can be stacked.
Exactly.
To 100, 150, 200, 250 kVA and so on?
Exactly. And with the LFP batteries, basically each of this inverter comes with a stack, and then we can basically do it like a vertical stacking of them. So that's very modular in design and can be done quite easily compared to what previously was done for lead acid batteries with battery strings and this complicated idea. And
these 50 kVA modules, at what price point do they come? Roughly, indicatively? I've got information that they are not far from $10,000 per piece. Like a little bit above maybe. But if you compare to single-phase inverters and clusters of those, this is definitely significantly cheaper. All right. And these 50 kVA modules, what battery voltage level do they usually support? When we look at these small single-phase inverters, 5 kVA, 6 kVA, 8 kVA, they usually come with 48 volt low voltage. My understanding is that this is not being supported by these larger batteries. The currents would be simply too high, right?
As Mike also mentioned, that nowadays LFP batteries are the preferred battery technology over lead acid batteries for mini grids. When lead acid batteries were mostly used, the battery string level voltage was like 48 volt on the DC side, right? Normally they would 24 numbers of 2 volt. Lead acid batteries were tied in series to make one large or long battery string. And then you would need such kind of strings in parallel to then attach to this cluster of battery inverters that we just discussed. Of course, these 48 volt systems have a higher current carrying capacity requirement because it's low voltage. But you could also argue that these are comparatively safer compared to its high voltage applications. So these were the norm at some point that was used. But nowadays we see that some 6 kilowatt hour, 8 kilowatt hour is used on a voltage level with LFP batteries that's more than 100. So that's already not less than 100 volt DC, but more than that. And as you stack up these battery modules, your DC level voltage also increases, and this goes in the range of 400 to 600 volt maximum. And this has certain benefits to do it in this way. Definitely, it's able to charge and discharge faster than a 48 volt system. And in mini grids where you need high power for a very short amount of time, this high voltage system is definitely better compared to a 48 volt systems. We are discussing about rural industrialization and productive use of energy in mini grids and so on. And yeah, compared to 48 volt systems, higher voltage systems are definitely better in that respect. Also, there is this issue of space utilization. So this kind of low voltage systems or 48 volt systems with lead-acid batteries that we have discussed, of course, needs some space because there are strings of batteries that are laid on the floor, like horizontally. And now with the LFP batteries, these are more vertically integrated or stacked up on top of one another. And yeah, much more space efficient, so to speak.
What may be interesting is the auxiliary components for higher voltage switch gears and so on. And lower currents are usually cheaper than those for lower voltage and higher currents, isn't it?
Exactly. So then this also has an impact on the cost side as well.
Yeah, but you already said that high voltage is also kind of dangerous. What precautions do you need to take care of when deploying a high voltage system?
Definitely, if we are discussing about the 400 to 600 volt range, it needs some additional safety measures. Nowadays, so containerized systems that come are already integrated with its own necessary safety protections. Of course, the battery management system should be integrated as we are discussing about the LFP batteries. There is also this discussion around using anti-static mat to provide like a discharge path for the self-discharge current. Right now, the high voltage system providers, they also ask that you do not keep the DC system on a floating level. Rather, you should ground it. So, for example, 48 volt system, you could keep it floating, but with high voltage LFP batteries, manufacturers recommend them they are properly grounded to make the operation safer.
Understood. Which, after all, means that these very, very low cost cells, as we said, like sometimes you can get cells in the $30 per kilowatt hour range when it comes to LFP, and especially when it comes to sodium ion battery technology. Those cells are then available, but if I understand you correctly, Dipta, you wouldn't recommend mini-grid companies to go and build their own 400 to 600 volt system from that, because that requires some additional expertise and safety precautions and so on.
Yeah, definitely not. The mini-grid developers should do it by themselves. For lead-acid battery systems, this was different because it was more like the approach of doing it yourself, that you install and design by yourself. But with LFP batteries, there are certain risks that we all are aware of. For example, the thermal
runaway, yeah.
Yeah, so this kind of issues to avoid that, and even thermal propagation. So it can easily get ignited from one cell to the another. There are some IC standards, for example, the 62619, which clearly outlines that what test a lithium battery should go through before it's used. So there are strict requirements on their operating range and how the battery management system should work. So therefore, I would not recommend that system integrators, particularly mini-grid operators, do it by themselves rather than take more integrated and commercially available systems that are in the market with the correct certifications and all the safety precautions.
And that is what our subsidiary Volta Labs, also based out of Germany, has special expertise in. Volta Labs tests lithium-ion battery systems for the European car industry. Therefore we know quite a bit about lithium-ion batteries here in INENSUS. And lithium-ion is definitely a field that will develop further. And it's good to say that LFP batteries are already much safer than NMC batteries. But the sodium-ion battery that is coming in the near future will even be safer. Like those things like propagation are very unlikely to happen in sodium ion, and therefore they are really well suited for the mini-grid sector with a relatively low risk of explosion and fire. Very interesting. So after all, if I understand you correctly, Mike and Dipta, mini-grid operators have the choice of either going for extremely low-cost batteries, getting the cells, getting a battery management, which you can buy off the shelf for some $60 or so for a battery system from China or from Europe or the United States, and then basically set up everything themselves, but then only on the 48-volt level. And there they can either go for the more expensive single-phase inverters and build clusters. That has got the advantage that even in the small ranges, these clusters are quite modular, and you can add clusters and you can reduce clusters with their respective battery strengths. Or alternatively, they go for the self-made kind of battery system plus a low-cost Chinese inverter, which usually depends heavily on fans for cooling and is very sensitive to dust. And Mike, you already said that usual lifetime in Kenya is, what did you say? 2 to 5 years or so. And that is probably mainly due to the dust that settles on the power electronic parts and due to the inverters that cool these parts. And then the third option would be to go for a low-cost, large-scale inverter like the one from ABB, the 50 kVA modules, and then go for a professional battery system that is manufactured, but then the battery system does not come at $100 per kilowatt hour anymore, but probably a multiple of that, because all the safety related aspects and all the certifications and all the testing and everything has to also be paid for. Yeah, so a difficult decision to take. What do you think, Mike and Dipta, in which setups, in which countries, which developers should use what technology?
Okay, for the technologies, especially for the inverters, I would say the bigger 50 kilowatt inverters makes more financial sense compared to smaller single phase. However, there is a downside when you're using the single phase inverters. However smaller, at the end of the day, the balance of system and also the components in the overall system design is more compared to 50 kVA inverter. So one downside I can say for the bigger inverters like the 50 kVA modules, in case for the inverter does happen to fail, the impact will be bigger in the 50 kVA compared to one of the single phase inverters failing.
That's true indeed. Dipta, what do you think? Which technology is best suited for whom?
For the large mini-grid developers who are working in multiple countries and really looking for scale, they can really take the benefit of this standardized large capacity inverters. So then all integrated with the battery management systems and high voltage lithium-ion batteries. So they can really help on reducing the price or keeping the price, because as we have discussed, it's still a multitude of $100 per kilowatt hour. But if we are talking about scale for large developers, they can definitely go on this route. So I will say very small developers who are just starting out and have not got the capacity or the skill that's needed to do this kind of clustering technology by themselves, they can also go for this standardized, like from ABB or from Huawei, that this kind of plug and play kind of systems that comes with inverters, with batteries and everything, this kind of systems. But those who are in the medium scale that are not on the same level as, for example, PowerGen and others, they can go for building it by themselves. That would probably be most cost efficient for them. and also provides them the flexibility to work with them. But I will say the other two extremes, like very small or upcoming developers who are yet to get some experience, and the large ones, they should go for more standardized works.
Yeah. After all, probably each company has to find its own way forward. There are pros and cons for each option. And yeah, well, I wouldn't say large or small or large pipeline or not. And it's difficult to give clear recommendations for sure. But probably there are mini grid sizes. Definitely, if you just have enough demand for a 20 kVA mini grid, you wouldn't go for a 50 kVA inverter, most probably. If you need to be modular in the small ranges, you probably rather go for the single phase inverters in clusters rather than the large modules. At the same time, if you have very rural settings, you may not want to use higher voltages and run the risk of the higher voltages. And especially like if you handle higher voltages, you probably also need more trained personnel. And if there's more trained and more costly personnel that needs to travel, this also incurs some cost for high voltage systems. But after all, yeah, there are so many aspects to consider on the operation side, on the CapEx side, on the OpEx side, and so on, that each company probably needs to take its own decision. All right, let's look downstream in a mini grid system, which is the distribution network. Dipta, how are distribution networks designed? There are low voltage, there are medium voltage. When do you deploy what type of distribution network?
Thanks, Nico. Usually in a low voltage scenario, the electricity is then distributed in a radial structure. That means with a low voltage distribution network, it's a certain distance that we can go without significant voltage drop. So if the households and all the customers are quite close together, then we can definitely go for a low voltage scenario. But if we are talking about a 5-kilometer radius where the customers are dispersed and not so close by themselves, then in that case, low voltage network may not work. Or in the case where there are 2 villages nearby, but let's say distance by some 2 kilometer, then also you have this limitation from low voltage just to have one generation plant and then distribute the electricity to those 2 villages.
In Africa and Asia and developing countries in general, you don't build the distribution networks with a lot of redundancy. In Europe, for example, we have a lot of meshed or ring type of networks where if one string fails, then the other string can take over the entire supply to the end customers. This also helps in maintenance. You can, for example, switch off a certain part of the distribution network without disconnecting the end customers from the network. This, however, also means that both lines, both angles of the ring need to have the full capacity to transfer the full amount of electricity to the customers, which means way too much capex for a developing country. You want to keep costs down. And therefore, as you said, Dipto, in developing countries, Africa and so on, you rather build array type of networks. Can you explain, Dipta, quickly how we at INENSUS design these types of distribution networks, what we recommend, like what line distance from the power station the productive user should have, like the maximum line distance, what maximum line distance commercial users should have with their respective power consumption, and to what extent we allow households, residential customers to be connected to the low voltage network.
Yeah, sure. Normally when we are designing low voltage networks from the generation side, particularly in a radial manner, the idea is that we want to keep all the connections within 1 kilometer radius. It can go to 1.5 kilometer radius as well, but then of course we will have to increase the conductor cross section just to see if we are within the voltage drop level. But we definitely recommend that the productive use and all the commercial uses are as close, maybe less than 500 meters from the generation plant. Sometimes it's not possible, and then we have to find a way that how we can use like larger cross-section cables to reduce the voltage drops. Just to provide an example, like sometimes in different localities, for example, in Namibia, the distribution side, we can go up to 6% voltage drop from the nominal level of 230 volt. And until the service connection, that means at the household level or the customer level, it can be another 2%. So in total, 8% voltage drop is allowed from this nominal value of 230 volt. And then all the design criteria then are around that we adhere to this particular requirements either in a local jurisdiction or in as per the IEC standards.
Sorry to interrupt you, Dipta. What we should say is that the -6 and +8% of voltage drop in Namibia is rather an outlier. Most countries actually apply the IEC standards, which allow ±10% and an additional up to -5% for other voltage drops. That is much better suited for mini grids, and we would rather like to avoid too narrow tolerances regarding the voltages. Please continue.
So then that's the idea that we take, and what kind of loads there are. If it's an productive users with three-phase line, the voltage level is much more sensitive compared to a household level one, and they should be as close as to the generation plant as possible.
Yeah, we usually say within a range of 500 meters or even less, we would connect productive users like mills or welding workshops or so. And then up to something like 1,000 meters, we allow commercial users to be connected. And above that, it can only be residential customers, right? Just as a rule of thumb. The problem is that in many cases, villages extend to beyond this 1,000 to 1,500 meter radius. And what do you do then? You can only go for medium voltage. How does that look like? You need to build another network, right? On top of the existing low voltage one, isn't it?
Exactly. Of course, for the medium voltage network, we need additional assets. Like you need to first step up the voltage level from 400 volt to a higher level, like let's say 11 kV, and then distribute the systems there. So you need additional line as well. What we do is to use the higher pole and then use the same pole just to take also the low voltage in a different height, of course, with a safe distance. That's one way we do it, but definitely needs longer poles, 9 meter, 11 meter poles, and then we distribute to the next level.
What type of material is being used here? It's like poles for overhead lines, it's lines. Have you ever seen any underground networks in mini grids?
I have not come across underground lines myself for mini grids, but it's mostly overhead lines, as I said, with some 13-meter poles.
In 2009, 2010, we built some underground lines in our first mini grids in Senegal because the ground was very sandy and poles didn't last for long and they bent all the time. So it was better to build underground lines, and digging was quite easy in sand. So that was one example I'm aware of. All the other mini grids I've seen all have overhead lines according to standards. What types of poles are being used in Africa, Dipta?
Right now, we see that wooden poles are quite used at this point of time. So also steel poles are used as well as the concrete poles, but not so much. It's mostly a choice between cost. Just to give an example, like a 9-meter wooden pole would cost you some $100, whereas steel poles of the same height will cost you twice as much almost.
Depending on the international steel prices, right?
Of course, it also varies. And if good quality, like treated wooden poles are available, it's definitely the most cost-efficient option for the market.
Which is not the case everywhere, right? In East Africa, there are a lot of pole manufacturers in country. Basically, in Tanzania, we have some, for example. In Sierra Leone, There were none. Wooden poles would have needed to be imported. And in that case, it was cheaper and lower cost to actually bring steel poles or concrete poles into the country.
Exactly. Some companies also tried with bamboo poles at some point to reduce the cost, but I think considering the sustainability of these poles and more stringent requirements from governments, ultimately people are now switching to wooden poles and, as you said, in some cases steel poles and concrete poles.
Have you experienced any price trends in steel poles, wooden poles, concrete poles over time?
Over time, I think their prices are to some extent constant. We have not seen like a significant price change in the market over time of this kind of poles. The conductor prices, of course, slightly depend on whatever you are using. It's an aluminum or copper, but the prices of the poles remain more or less concrete. On the other hand, concrete poles themselves, and they would, if they're locally built, they would depend on the energy prices. But other than that, I have seen, for example, in Namibia, I can give an example, like 9-meter wooden pole costs something around like $85, $90. Whereas over the last 3-4 years, we have seen similar in other countries like Kenya, Sierra Leone as well. So it's in that range.
All right. And we've discussed medium voltage, and there are some mini grids with medium voltage, but according to our experience, and Jomema, our subsidiary in Tanzania, is operating medium voltage networks for some 8 years or so now. And we've seen that this really incurs a lot of OPEX. The transformers break, need to be repaired, oil needs to be exchanged. Lightning strikes into the medium voltage network always cause a lot of harm and destroy networks, cut off certain parts of the consumers for a longer period of time until everything's repaired. So therefore, there is now a new technology that's coming up, which is a technology of basically distributing the generation asset across the network and letting these inverter, solar, battery nodes communicate with each other. How does that exactly work?
Yeah, right now, as you said, Nico, so this kind of mesh network is coming up. And the idea is that these nodes will provide support to the rather large, like a central plant. And this will help in many ways. We have discussed the voltage drop issue. And it also provides ways to keep on providing the electricity to the customers if needed, isolating them and providing them, but also reducing the conductor cross sections that needed, and also the need to upgrade to a medium voltage line potentially. Yeah? So that's what we have discussed, that with medium voltage line, we always have these different issues, but reducing the cross section and also adhering to the voltage drop regulations. So then this kind of mesh network can provide like an way to do that.
Yeah, and that brings us back to our earlier discussion. If you go for smaller individual nodes, you may then use the lower cost 48 volt self-made lithium ion battery systems and connect them to one cluster of battery inverter and then AC couple the PV generation plant of whatever, 5, 10 kilowatt peak or so, or even 20 as a node. And this significantly reduces, as you said, the cross-section of the aluminium cable, the conductors, and that significantly again reduces the overall capex for the distribution network. This mesh network, or some call it swarm approach, is really a very nice idea that is currently being developed bottom up. It's more or less coming from the solar home systems range, and the idea was to interconnect solar home systems initially, then AC mesh networks were developed, and now I understand that the nodes that are being offered are getting larger and larger. The interesting part would be to investigate more on which inverters can be used for this mesh network. But I guess that is what we'll have a separate episode on, and discuss the new mesh network approach in more detail.
Yeah, I also actually did my master thesis on this, on doing this mesh networks, and we have tested this and simulated different options. But I also agree that there are now more companies that are looking into this. And initially, these were like, as you said, in solar home systems was done. So these were kept with like less than 100 volt DC level. So it could be distributed quite easily, doesn't need that many quality poles with stringent requirements. With AC, we will need that, but this is a very interesting topic, and we should look forward to that, how this will change the distribution landscape.
Yeah, indeed. All right, let's move one step further downstream and talk about the meter market. Mike, we've seen some movement on the meter market over recent years, from classic postpaid meters to prepaid meters and then to smart meters. Do you want to talk more about that?
Yes, sure. So meters in the context of mini grids, crucial for measuring the electricity consumption and facilitating the actual billing of power generated. So as Nico mentioned, we have the conventional, which are the postpaid and the prepaid meters, and smart meters. When choosing the meter, it's influenced by several factors: the payment model the mini grid developer chooses, the visibility on the energy consumption of the data, and the cost. Smart meters currently are favored due to the ability to measure and communicate payment and consumption data remotely. However, it's typically more expensive compared to the conventional meters and dependent on the reliable mobile network connectivity. So cost on the meters for mini grids varies based on the type and the capabilities. As mentioned, that's for the postpaid and prepaid models are generally less expensive and simpler in design. Smart meters, on the other side, offer advanced features like remote monitoring, data communication, and tend to be more costly. The choice between these depends mainly on the budget constraints of the developer and also the desired features. So currently in the market, we have spark meters, Stimaco, and Carlin meters, which on the cost side, Carlin is the cheapest among the three, around $22, and the Stimaco is around $50, so averagely $30-something on average. And the cost of the meters is expected to lower because Stimaco and Spark meter currently are shifting to Chinese large manufacturing hubs. In INENSUS, we have been working with meters since 2015. Yeah, so we have the Micro Power Manager platform, which can be able to integrate with the 3 meter models mentioned.
And even more. we are integrated with many more meters, indeed. Uh-huh.
Yes, when you're looking at reliability of the said meters in the mini grid system depend on the type and environment in which they operate. Conventional meters, being simpler in design, often have fewer failure points and generally reliable in various conditions. However, they lack advanced features and require manual reading and maintenance. Smart meters offering remote monitoring and management can enhance operational efficiency. Still, their reliability is contingent on factors like stability of the internet or the mobile network connections and susceptibility to technical issues. We can generally say the choice between the conventional meters and smart meters will depend on a balance between the desired features and the practical aspects of the particular operating environment.
Yeah, and when it comes to smart meters, some 10 years, 8 years, 5 years back, maybe even, the main issue was the last mile connection through LoRa networks, through mesh networks, Zigbee, and other type of proprietary networks. That has not worked very reliably, but I understand that this challenge has now been overcome, and now smart meters are connected quite reliably, even if they are a little bit dispersed and distributed within a relatively large village. So that is not an issue anymore. Other than that, of course, there's a big price range between, on the lowest end, prepaid meters for $15 can be purchased from China, single phase, whereas the smart meters are more in the range of $50. And as the average revenue per customer in a mini grid is usually somewhere at maybe $4 to $6. Of course, it takes a lot of time to amortize a $50 meter. Anyway, there are big advantages, as you already said, Mike. Last but not least, Dipta, there are different types of powerhouses. some companies really count on solar containers that can be shipped, readily equipped, readily installed, more or less. You put them onto a foundation and then you connect and off you go. Others say, well, this is too expensive. I am cheaper if I build my powerhouses myself. And then we can also involve the local population. And even others go for prefab structures where you basically ship complete walls and then you mount the walls on a ready-made foundation on site. What is your experience here, Dipta, and what works where?
Yeah, nowadays we see that more and more developers are using this kind of solar containers. We have mentioned this kind of integrated system designs with LFP batteries and so on. So this is getting more common in Nigeria, in Uganda also. Just to provide an idea to the audience, a 50-60 kilowatt system can easily fit into a 20-feet container. Whereas like if we're talking about some 100-120 kilowatt systems, this will need a more spacious 40-feet containers. And these containers are standardized containers, so then nothing special about them. Of course, this comes with a much cheaper price compared to other type of constructions. They can a few $1,000s, you can easily get them. Yeah. And this is getting quite standardized in use, and we see more and more developers using them. But also, a few developers like PowerGen, for example, started with this containerized idea and now rather shifting towards locally building the powerhouses themselves, because with fully integrated container, we see this is very difficult to transport to the project sites. Rather, building themselves bottom up is easier and in some cases cost effective as well. Whereas for INENSUS, we actually did the opposite way. We actually started with building the powerhouses, but there are like field realities that we see that it's difficult to get everything done. Sometimes the workmanship also suffers. But yeah, in my opinion, there is no one-size-fits-all solution here. It depends a lot on the field reality, the road infrastructure, if everything is in order or not. At some point in Sierra Leone, we actually also tried these prefab shelters, as you mentioned, as powerhouses. But we also see from our experience that after all, these were not very highly suitable for rainy areas and so on, particularly Sierra Leone. But yeah, there are three options. It's an matter of like cost optimization, but at the same time, how you will install it and what difficulty you will face to do that, considering the sustainability of them later on.
Exactly. Logistics. How do you offload the container on site? How heavy is the container when you offload it on site? Do you need a crane? As you said, on the islands in Lake Victoria, where Jumema installs their systems, bringing a complete container is not an option in most cases. The harbors are not made for that. In some cases, islands don't have harbors at all. There we had to definitely construct powerhouses with the local people. And that was also well received by the local community that then could earn some money by providing labor to that construction site. Mike, we have not talked about DC systems like direct current systems. Are you aware of any direct current systems in larger mini grid these days?
Yes, we have the Okra mesh grid system that utilizes DC system, and what we have seen is as the system size gets smaller, you'll be able to witness more of the DC systems. And normally DC systems work best where there is a dense customer base and they utilize smaller systems like solar home systems. And normally using the solar home system, they use the peer-to-peer trading networks. For instance, the Okra network have access to 600 and 1200 watt DC power by plugging into the Okra pods. And using this system, Okra provides power on an energy as a service basis. These systems normally are designed to connect to form a network and ensure the developers who deploy these networks are incentivized to keep the network operating smoothly and sustainably. So when you're looking at the main advantage of DC systems, I would say it will be the cost per connection, which is usually around $120, while we are looking at AC system, it can go for around $1,200 per customer connection.
So if I understand you correctly, Mike, we may be seeing a revival of DC systems as the mini-grid design is moving from a central generation to a decentralized generation setup with individual nodes, which can be potentially designed at a lower cost if you select DC systems, smaller DC systems. Interesting. Looking forward to see what the future brings. And that is my last question to you, Dipta and Mike. What do you think the future holds for mini-grid technology? What do you think will the mini-grid technology look like some 5 years from now?
I would say for starters, when you're looking at the main component, that's the panels, battery, and inverters, the efficiency of the solar panels on a yearly basis, it's increasing, and also the cost is continuing reducing. So I would say on the components aspect will be more efficient equipment and lower costs. And also on the technology aspect, especially when you're talking about the Chinese and European brands. So due to the competition, we'll witness a specialization, especially because European brands might prioritize high-end residential and commercial application, while Chinese brand, which is currently more common, will focus on large-scale utility projects and also look at the emerging markets, which are mainly focused on the cost aspect due to the client base. And I would say on meters, which the market is evolving rapidly, smart meters particularly, the solar-specific ones, will see an increased adoption due to the advanced features and ability to support growth of renewable energy.
All right, Dipta, what is your take on this?
I will say that we get more and more standardized systems that can really work plug and play. And also what we in INENSUS say, like running the systems on autopilot, I think we will move towards that. We will move towards, in 5 years, hopefully, in like a fully diesel generator free mini grids running mostly with LFP batteries, and possibly, as we have discussed, sodium batteries will be its competitors. So the other way around it was before for lead acid and LFP batteries. And at the same time, we will possibly see this kind of mesh networks so that we can connect more customers with a low cost of connection. That's how I see it. But yeah, I think we are moving towards rather a cost-effective solution and see where the limit is.
Cool. Sounds good. Dipta, sounds good. Mike, this sounds very promising. Sounds like there are big cost reductions and efficiency gains ahead. And this will not only reduce the tariff, but it also will help rolling out mini grids across the continent, potentially reducing the grants required and convincing more governments to deploy mini grids operated by private sector across the continent. And I'm really looking forward to experiencing that in the coming years. And INENSUS will, of course, continue to play a strong role on the communication side and also on the design side. Thanks a lot, Mike. Thanks a lot, Dipta. This was great fun. Talk to you soon.
Thank you.
Yeah, thanks for having me.
This episode of the Mini Grid Business has been brought to you by INENSUS, your one-stop shop for sustainable mini grids. For more information on how to make mini grids work, visit our website, INENSUS.com, or contact us through the links in the show notes. The Mini Grid Business, powered by INENSUS.